Hello guys and girls, welcome to this Karpenter course. If you are someone who is looking to learn Karpenter, the latest Kubernetes Autoscaler, this course is for you. This course will teach you the fundamentals and set you up for more intermediate and advanced concept. We are going to cover Kubernetes scaling fundamentals, cluster autoscaler challenges, Karpenter, what and why, NodePool, what and why, Kubernetes scheduling with Karpenter, along with a demo and how do you save cost with Karpenter consolidation. For those of you who are new to this channel, my name is Rajdeep Saha. I'm a L7 Principal Solutions Architect working at AWS for the last 5 years. I'm also a best-selling author, recipient of the Top Systems Design Award by LinkedIn, public speaker, and YouTuber. All right, let's get started. Let's start by understanding how does Kubernetes clusters scale. What are we really trying to do at the end of the day? Well, your application is running in a Kubernetes cluster in a worker node running in a data plane. As the traffic increases, all we are trying to do is going from left to right, scaling from one EC2 instance to multiple EC2 instances, running your workload and serving a higher amount of traffic. So let's zoom in. In the data plane, you have worker nodes running, which could be a virtual machine such as Amazon EC2. Inside this Amazon EC2, you have one or multiple pods running. Inside each pod, you have application container running. Pod is the smallest unit of work in Kubernetes, so that's what we are going to go by. So how do you expose this pod? So this pod running inside Amazon EC2 and serving traffic using a service. Now, this pod has some amount of resources allocated, CPU, memory, etc. So let's say there is some traffic coming into the pod and this pod is serving that traffic and the CPU utilization is around 30%. Now to scale this pod, you use horizontal pod autoscaler or HPA. HPA is set on a deployment. So you will say something like scale the number of pods if the deployment pod CPU goes over 50%. It's important to keep in mind that the CPU utilization is for the whole deployment. So if there is only one pod currently running under the deployment, then it goes by the CPU of this pod. But if there are multiple pods running, horizontal pod autoscaler will look at the average CPU utilization of the whole deployment across all these pods. And if it is more than 50%, it will increase the number of replicas in that deployment. And even though in this example, I'm just showing CPU, you can trigger HPA based on memory and other metrics as well. All right, so let's say at this point, the traffic increases. So the CPU utilization for this one running pod increases to 80%, which is greater than 50%. So at this point, HPA will increase the number of replica by 1. So it creates one additional pod and all pods starts with the status pending. And then kube scheduler or scheduler, which is running in the Kubernetes control plane, comes in and the scheduler tries to find a node for this pending pod. In this case, the running Amazon EC2 has some capacity left. So scheduler will see there is some capacity available in existing EC2 and it will schedule the pod and the pod status will go from pending to running. And then this second pod will also serve traffic and the average CPU utilization will go down. Now let's say traffic keeps on increasing and then the average CPU utilization for these pods go above 50% again. But at this point, this Amazon EC2 is out of resources as well. Let's say the Amazon EC2 CPU is at 90%. But HPA does not know that. HPA's job is simply to increase the number of replica in the deployment based on some metrics, in this case CPU. So HPA simply increases the number of pods, which causes the pod go to pending. Scheduler then jumps in and says, where do I put this pod? But hold on a second, no capacity is available in existing EC2. So the scheduler cannot really schedule this pod into the running EC2s. And scheduler cannot really scale EC2s. That's not scheduler's job. So at that point, that pod becomes status pending and also unschedulable. This is where Kubernetes node scalers come in. So node scalers such as cluster autoscalers or Karpenter, they also periodically check for any pending unschedulable pods. Anytime they find a pending unschedulable pod, they will scale the virtual machines. So let's say in the previous example, there was a pending unschedulable pod. Node scaler sees that, creates a virtual machine. Also, the scheduler keeps on trying to schedule this pod. As soon as this virtual machine comes up, scheduler sees there is some new capacity and then schedules that pod in that newly provisioned virtual machine, and the pod status becomes running, and then it starts serving the additional traffic. Throughout this course, we are going to use a simplified flow. So the pod goes to pending, scheduler checks, where do I put this pod? No existing EC2s is available. So then node autoscaler comes in, scales node, new EC2s come up, and the scheduler then schedules that pod into the new EC2, and the pod status becomes running. Even though I'm showing scheduler and then the arrow going to node autoscaler, don't think that scheduler is calling the node autoscaler, right? Because we saw in the previous slide, node autoscaler is periodically checking for pending unschedulable pods, and scheduler's job is just to schedule a pending pod into a node. I wanted to touch on another scenario. So the scenario we just discussed using horizontal pod autoscaler and the node scaler is very, very common for microservices. But in some cases, you may be running your Kubernetes pods as batch jobs. So let's take an example. Let's say you run this deployment, which is deploying 4 replicas of this deployment. And let's say this deployment runs batch job. So this is not really triggered by horizontal pod autoscaler. So at this point, as soon as you deploy that deployment, 4 pods goes to the status pending. Scheduler comes in and says, where do I put this pod? And then it finds the space for 2 of this pod in the already existing running EC2 instances, assuming that each EC2 can run only 2 of these pods. And the remaining 2 pods goes to the status pending with condition unschedulable. So then the same flow takes over. Remember, the node scalers keep on checking for pending unschedulable pods. So as soon as it sees that, it will create a new Amazon EC2, and then scheduler see there is space for these 2 pending unschedulable pods in this newly provisioned EC2, and it will schedule those and they will start running. Takeaway here is the node autoscalers create new nodes whenever there is a pending unschedulable pods. All right, now that we understand the Kubernetes scaling fundamental, let's take a look at one of the very, very popular node autoscaler, cluster autoscaler, in the next lecture. Welcome guys and girls to this lecture. In this lecture, we're going to talk about the previous Kubernetes node autoscaler, which is cluster autoscaler, and some of its challenges. Chances are a lot of customers are still using cluster autoscaler, and it is important to understand the challenges of it. Because only after we understand the challenges, we will understand why was Karpenter created in the first place, as well as the benefits and superpowers of Karpenter. All right, let's get started. So to use cluster autoscaler, you need to create node groups. And to create a node group, you need to specify what types of EC2 should be in a node group. That's why I specifically put this A in parentheses within EC2s. One node group can only have EC2 instance type of same memory and same CPU. And this node group will be tied to an autoscaling group. Also, you need to specify beforehand what EC2 instance types should be in this node group. So let's say you created 3 different node groups, node group A, node group B, and node group B again has different types of EC2s, and node group B is tied to autoscaling group B, and then node group C, again, which has different types of EC2s tied to autoscaling group C. And how does the autoscaling flow look like for cluster autoscaler? We already know the general flow. As soon as a pod goes to pending unschedulable, cluster autoscaler gets triggered. And in this case, cluster autoscaler will scale the autoscaling group that's tied to a node group. So a new EC2 will come up in that node group, and then scheduler will put that pending unschedulable pod into this new EC2, and the pod status will be running, and all the pods will be serving the incoming traffic. So what are some of the challenges? First is node provision latency. So the pending unschedulable pod triggers cluster autoscaler, and that triggers the autoscaling group. And the autoscaling group invokes EC2 API, which provisions the Amazon EC2, and then the pod gets scheduled in that EC2. So starting from the pending unschedulable pod to the EC2 being provisioned takes minutes, because it's not a direct EC2 API call. For every time cluster autoscaler needs to provision EC2, it needs to interact to this autoscaling group. And the autoscaling group interacts with EC2 API as well as node group. So there are multiple hops here. Now let's take a look at Karpenter. Karpenter bypasses this whole node group and autoscaling group and directly calls EC2 API in response to pending unschedulable pod. And a Amazon EC2 is created and the pod gets scheduled there. Also, Karpenter does not need to use any node group. And because Karpenter directly invokes EC2 API, the process from pending unschedulable pod to provisioning an EC2 takes seconds instead of minutes. Now the bigger challenge with cluster autoscaler is node group management. Remember, we said that you need to have node groups, and then each node group can only have compatible EC2 instance type, and you also have to specify what EC2 instance type should be in that node group. So let's say you have a compute node group running which has m5.large EC2 instances, and then an application deploys a GPU workload which requires GPU instances. But GPU instances cannot be associated with this compute node group with m5.large instances. So this GPU workload will not get scheduled. They will stay on pending. So what is the workaround? Workaround is the Kubernetes admin needs to log in, creates a new GPU node group which will have GPU instance types such as P4 or P5, and then a new P4D instance type will come up, and then only this GPU workload will get scheduled. So think about this. Every time there is a new workload which requires a new instance type which is not included in any of the existing node groups, you need to either update the existing node groups or create a new node group. And over time, you may have multiple node groups, which creates management overhead. With Karpenter, there is no node group, and Karpenter can automatically choose from all instance types. You do not need to specify certain instance types that need to be used. You can if you want, and we'll see this down the line. And if you need to update it, it's way simpler. So with Karpenter, let's say you have all your pods running in a C5.2x large, and then an application team deploys a GPU workload. Not a problem. Karpenter will intelligently spin up an appropriate GPU instance such as P4D and deploys this GPU workload in that instance. So Karpenter can provision appropriate instances based on your pod specification file without the need of creating and managing node groups. And again, keep in mind, with autoscaling group, node group with cluster autoscaler, only compatible instance types can be used. So Karpenter is fast, and Karpenter also does not have the management overhead of managing node groups. All right, now that we understand the cluster autoscaling challenges and how Karpenter solves them, let's do a proper introduction of Karpenter in the next lecture. All right, so let's properly introduce Karpenter. So what is Karpenter? Karpenter is an efficient node autoscaler for Kubernetes. Karpenter scales the worker nodes, and it does it faster than existing cluster autoscaler. Karpenter can automatically launch appropriate worker nodes without creating or managing any node groups. Karpenter is created by AWS. However, Karpenter is open source. AWS donated Karpenter to CNCF, and it is one of the CNCF projects now under SIG autoscaling. So it is important to note that anyone can open source a project, but getting accepted by CNCF is prestigious. There are thousands of open source projects, but only limited number of CNCF accepted projects. Karpenter is also adopted by Azure. Karpenter is Kubernetes native. Karpenter supports YAML and it respects Kubernetes scheduling. Now, I'm just gently introducing the concept, so I'm pretty sure this Karpenter Kubernetes native part is not clear, and I promise that as we go through this course, all of this will become crystal clear. So scaling is bread and butter of Karpenter. But Karpenter does more than scaling. Karpenter helps in optimizing cost. Karpenter supports diverse workloads, including machine learning and generative AI workloads. Karpenter helps upgrade and patching, and Karpenter is Kubernetes native. And don't worry, we are going to go through each of these points in more details in the upcoming lectures. Because of all these features, Karpenter does a total data plane implementation. Cluster Autoscaler just does scaling. So as you could see, Karpenter does more than scaling. And Karpenter is part of Kubernetes, the open source software ecosystem. All right, that's it for this one. Let's dive deeper into the Karpenter concepts. Welcome guys and girls to this lecture. This is one of the most important lectures of this course. In this lecture, we're going to learn about NodePool YAML. When it comes to Karpenter, you can control its behavior using two YAML files. The first one is NodePool, and till a previous version, this file was known as provisioner, and the other file is EC2 node class. Similarly, until a previous version, this was known as AWS node template. However, NodePool and EC2 node class is the new and permanent name, and that's what we are going to use throughout this course. In this lecture, let's take a look at NodePool. So let's look at what does a container need in order to run. CPU, memory, storage, network, and sometimes GPU, and then you scale your container based on one of these metrics, CPU, memory, or perhaps some custom metrics. At the end of the day, all we are trying to do, or the objective of Autoscaler, is select an appropriate EC2 instance type for this pod to run. But the challenge is there are over 300 different instance types that AWS provides. So if we look at a EC2 naming convention, the first letter signifies the instance family, and this instance family represents the CPU to memory ratio, and then we have instance generation, then additional capabilities, and then the instance size. The instance size represents the amount of CPU you get, and then since the CPU and memory follow some proportional ratio based on the instance family, the larger the instance, the more CPU and more memory you get. And all this creates the instance type. And containers are flexible. They can bin pack to different instances, as in multiple pods can run in one instance and maximize the resource consumption of the instances. While this is a great advantage, it also complicates the instance selection and orchestration. Fortunately, Karpenter can automatically select the best instance type based on your workload and scheduling constraint, or on the other side, you can also control what kind of instance types and what other controls you want to place if you need to. We do that using a file called NodePool. This is a YAML file. It can define what kind of nodes or EC2 instance type Karpenter will create. You can define instance type, CPU architecture, such as Graviton or x86, number of cores that the EC2 instances must have, certain availability zones for nodes that Karpenter will respect. You can have one or multiple node pools per Karpenter installation, and we'll go over this a little bit later. So where does this NodePool file fall in the autoscaling flow? So if we go back to the previous scenario, if a pod is pending and kubescheduler is looking to see where can it put this pod, and there is no existing EC2 capacity available, and scheduler marks this pending pod as unschedulable, and at this point we know that's where Karpenter comes into play. anytime there is a pending unschedulable pod, Karpenter needs to provision a EC2 instance. And Karpenter is going to check this NodePool file, and this NodePool file will specify what type of EC2 instances it should consider along with some of the other properties. And then the Karpenter will pick the most appropriate EC2 instance type from that list that's specified in the NodePool, and then it will create a new EC2, and then the pod will get scheduled in the new EC2 with the status running. All right, so now that we understand the flow, let's take a look at an actual NodePool file example, and things will become even more clear. So on the right is the YAML, the kind is NodePool, and then we have a name. Let's say for this NodePool, the name is team-A. Now the important part is under spec::requirements. This is where you can define the requirements. And I mentioned you can, it is not required. And when you define the requirements, you have multiple options to choose from. So in this case, we are putting karpenter.k8s.aws/instance family in C5, M5, R5. So any EC2 instance that this Karpenter NodePool provision must be within C5 or M5 or R5. The instance size must not be in nano, micro, or small. And these are just couple operators I'm showing. You can also use greater than, less than, etc. Also, in certain scenarios, if you already know exactly what instance type your application should run in, you can also specify that directly in the NodePool. So in this case, I'm specifying instance type in m5d.extra-large or c6a.large. When this NodePool provisions instance, it can only be between these two types. And if I have specified just one type, Karpenter will only provision that specific instance type of instances. Now remember I said these fields are optional. If you do not give any list, Karpenter will pick from all instance types in EC2 universe excluding metal. You can also limit how many EC2 instances this NodePool can provision. So on the bottom, you have CPU as 100 and memory as 1000 GB bytes. So this NodePool can keep on provisioning EC2 instances till the combined CPU cores reaches 100 or combined memory reaches 1000 GB byte for all the EC2 instances that this NodePool provision. NodePool can also define the availability zones where the EC2 instances must be provisioned. If you do not put any availability zone, it will provision in any AZ that's available. Or you could say only provision EC2s in specific availability zone, in this case US West 2A or US West 2B. You can also define CPU architecture. So for example, with x86, you can put AMD 64 or ARM 64, which is ARM instance or Graviton instance. Now this is another superpower of Karpenter, the purchase option flexibility. This capacity type specifies whether you want spot or on demand. If you don't specify this parameter at all, it will always provision on demand instances. If you specify spot, on demand, it will automatically prioritize spot, and it will always try to provision a spot instance, and it is intelligent enough to know if spot is cheaper than on demand. So let's say you put spot, on demand, but let's say for some reason on demand is cheaper than the spot, and the Karpenter in that case will provision a on demand instance instead of spot. So these are few of the main things that you could control using NodePool. Throughout this course, we will look at various fields and how to use them in NodePool. I just want to give you another quick glimpse from official Karpenter documentation to show some of the other operators. Let's say in this sample NodePool, you can also mention instance hypervisor in Nitro. You could put instance generation greater than 2, as in greater than second generation, and we already went to the zone, architecture, capacity type, etc. If you put multiple of these options in this node pool, or let's say you skip everything, right? So if you don't put this instance category, then Karpenter is going to evaluate all available different instance types. This is the beauty of Karpenter. Karpenter will automatically choose the best instance type. In your pod specification file, you will mention some requested CPU and memory along with Kubernetes scheduling constraints. Karpenter will take all that into consideration and create the best EC2 instance type for you. And even if you specify these instance types, if we go back to our cluster autoscaler example, and tomorrow you need to add another new instance type, you don't need to go through creating another node group, another autoscaling group, etc. You can simply come to this node pool and simply add an instance type here, and that's it. All right, that's it for this one. I'll see you guys and girls in the next lecture. Bye. Welcome guys and girls to another lecture. In this lecture, we're going to understand how Karpenter works with Kubernetes scheduling. Before we jump into the Karpenter part, let's quickly talk about Kubernetes scheduling. So what does it mean by Kubernetes scheduling? So anytime a pod goes to a pending state, it could be that horizontal pod autoscaler is scaling out and creating new pods. Could be an existing pod gets terminated or a whole node gets terminated for some reason. So new pods come up. And then the Kubernetes scheduler or kube scheduler finds out where or which node should this pod be scheduled. That's what Kubernetes scheduling means. Let's say in this case, there are two EC2 worker nodes, worker node 1, worker node 2. Worker node 2 is a bigger worker node with more capacity available. And then a pod goes to pending. And then the kube scheduler thinks what is the best node to put this pod. And then it determines that maybe worker node 2 has more capacity. So I'm just going to put the pod there. So the official definition is the Kubernetes scheduler is a control plane process which assigns pods to nodes. The scheduler determines which nodes are valid placements for each pod in the scheduling queue according to the constraints and available resources. Then the scheduler ranks each valid node and then selects a node and binds the pod to a suitable node. So this is out of the box. If there is nothing special going on with the pod specification file, the scheduler puts that into worker node 2. This is just for an example, right? But in reality, application teams want to control Kubernetes schedule so that the scheduler don't just randomly put the pods in any available nodes. Maybe application team wants their pods to be scheduled in specific setup nodes. So why control Kubernetes schedule? So let's say, for example, you want to run certain workloads in certain EC2 instance type. It is a non-critical, maybe CI/CD workload. You want to run those in spot EC2 instances. If it is a graphics workload, you want to run them on GPU, Graviton, etc. You want to make workload highly available. If you have two replicas of one pod, and if you leave it up to Kubernetes scheduler, it's possible that it can schedule both pods into a same EC2 instance or a single EC2 instance, but then it will not be highly available, right? Because if that availability zone goes down, that EC2 will go down, both pods will go down. To make it highly available, one pod should go to EC2 instance in one availability zone, another pod should go to another availability zone. So you control that using scheduling constraints like topology spread. Or perhaps you want to run certain workloads for one team in separate worker nodes. Maybe that team has a compute savings plan or reserved instances or specific hardware needs or security isolation needs, etc. So how do you implement that in Kubernetes? So one of the common way to do that is using a node selector. So let's go back to the previous example. So you have a pod, but now we have this added constraint that this pod will only get scheduled on EC2 nodes where you have this label team:team A. So you use labels to schedule pods for different applications. previous scenario, we saw that the scheduler put that pod on the worker node 2 because maybe it determined worker node 2 has more capacity. Also remember that Kubernetes labels are not AWS EC2 tags, right? The Kubernetes labels are Kubernetes constructs. They are not AWS constructs. Now, how do you figure out what labels these nodes have? You can run this command kubectl get nodes -- show labels. It will show the label. And let's say in this case, only worker node 1 has this label team equals to team A. So where will the kube scheduler schedule this pod? Still worker node 2 or worker node 1? Well, you guessed it right. It will schedule it in worker node 1 because now we are controlling the scheduling using this node selector and node labels. And labels are just one of the available Kubernetes scheduling constraint. You can also control scheduling using annotation and taints. So now the question is, who puts label on the node? So you can, of course, assign label after these nodes are created, but then that's like a manual ad hoc process. So ideally, the labels or annotation or taints, they should be added during the node provisioning, right? When the node is getting created, you should attach all the labels, annotation, and taints. So which process controls what kind of EC2 instances should be provisioned? Karpenter NodePool YAML. So as it stands, using NodePool, you can attach this label, annotation, and taints. So this is an example. On the left, you see a NodePool, and then it has the annotation part, label part, and taints part. So any EC2 instance that this NodePool provisions will have these taints, labels, annotations added. And then on the right, we have a sample pod specification files. So it could be used to schedule the pods accordingly. One pro tip is the name of the NodePool specified by this name : team A. This NodePool name will be automatically added as label to the EC2 instances provision. So if you have multiple NodePool, each EC2 instance provisioned by those NodePools will have the label as the NodePool name. So you can always use the NodePool name to schedule the pods, but that's not the best practice. You should always use some custom label or taints or annotations. Karpenter also automatically adds well-known labels to the node. So you do not need to put this in the NodePool. If a Karpenter provisions a EC2 instance in, let's say, US East 2A, even if in NodePool you do not specify any availability zone, does not matter. Karpenter will add the label topology.kubernetes.io/zone as US East 2A. Similarly, instance type, operating system, architecture, etc. It will put all those labels. So I'll give the link on the bottom. These are sample well-known labels. So what that means is, in your pod specification file, you can use this label to schedule your pods to specific nodes. Now let's take a look at a common example, which is availability zone scheduling. So let's say on the right, we have the NodePool, and it says that EC2s must be provisioned in availability zone either US 2A or US 2B. Now let's say pod specification comes up, and the pod specification file says that the node selector is topology.kubernetes.io/zone is US West 2A. And if this pod goes to pending and there is no existing EC2 in US West 2A, Karpenter will provision an EC2 instance in US West 2A. So this pod scheduling constraints must fall within the NodePool scheduling constraints. If the pod scheduling constraint has US West 2A, but let's say the NodePool does not have US West 2A, the NodePool, let's say, just have US West 2B, then this pod cannot be scheduled because this NodePool can only provision nodes on the availability zone that is specified in the node pool, if you choose to specify it. If you don't specify availability zone, then it will of course schedule it in US West 2A. Okay, let's take another example. Let's say this is the node pool on the left, and let's say it provisions EC2 instance with capacity type spot and architecture type x86, which is AMD 64. As it provisions these nodes, these labels will be added to the nodes. So that means you can use those labels to schedule other pods. So let's say we have this another pod specification file where we are using node affinity, and then we are using required during scheduling, ignored during execution, and must match expression carpenter.sh/capacity type in spot. So since we put required during scheduling, ignored during execution, this expression must be matched before scheduling. So in this case, the pod is using this label that's attached to the EC2 provisioned by the Karpenter node pool, and it will schedule that in the EC2. So utilize node selector, node affinity to schedule pods into appropriate nodes. Now Karpenter also supports GPU. So let's say on the left you have a sample pod specification file where you put resources limits nvidia.com/GPU1. And on the right you have the node pool, and you have the carpenter.kubernetes.aws/instance family in P3. So to satisfy this nvidia.com GPU, so the instance family must have the nvidia.com GPUs. But you don't need to specify nvidia.com/GPU on the node pool. There are also other GPU values supported, such as amd.com/GPU, amazon.com/neuron, habana.ai/gaudi, etc. Now with GPU, you do need a couple of extra steps. You need to install device plugin and etc. This is the link. But I just wanted to highlight that Karpenter also supports GPU scheduling requirements out of the box. Karpenter also works with taints and toleration. Setting a taint on a node tells the scheduler to not run a pod on it unless the pod has explicitly said it can tolerate that taint. So in this example on the right, we have a node pool which provisions GPU instances such as P3, and it attaches taints to those nodes. So only pods that can run in that node must be the pod which requires a GPU to run. And this is specified by this key nvidia.com/GPU, value true. So how can a pod run on this node, or how can a pod trigger provisioning a EC2 node like this P3 on this node pool? So that's the pod specification file on the left. So we have put request nvidia.com/GPU. That means that it will request a P3 instance from the node pool, but that's not enough because now we have the taint. So the pod to run on this node, it should also have the toleration. So the toleration, the key should be the same as the taint, nvidia.com/GPU operator exists. So okay, so you can see that Karpenter also respects taints and tolerations. And finally, looking at an example of topology spread with Karpenter. So on the right, we have a sample node pool. Every EC2 that's provisioned by this node pool is going to attach the label appteam:/team-a. A very important factor for topology spread is availability zone. So under zone, we are going to use US West 2A and US West 2B. And on the left is the topology spread constraints on the pod. So basically we are using this topology kubernetes.io/zone parameter with the max Q1. We're also using the label selector. It should match the label appteam:/team-a. All right, so as you could see that Kubernetes supports various scheduling mechanisms such as node selector, node affinity, taints toleration, topology spread, and Karpenter respects all of it. Using Karpenter YAML and then pod scheduling constraint, you can granularly control where your workload runs. All right, hopefully now it is making sense that how closely Karpenter is integrated with Kubernetes, how much flexibility it gives you on working with different Kubernetes scheduling constraints, and that is the reason why I mentioned Karpenter is indeed Kubernetes native. Alright folks, that's it for this one. I'll see you guys and girls in the next one. Bye. Welcome guys and girls to the first demo video of this course. In this video, we are going to learn how to install Karpenter as well as how to run it. For this demo, I'm going to follow the official Karpenter documentation because you know one thing about Kubernetes is it changes. So I'm going to just go through the official documentation so that you know how to follow it. So even down the line, anything changes, if you know how to do it from the official documentation, you will be able to install it even the next versions. All right, to find the official Karpenter documentation, you can just search Karpenter and click the first link, karpenter.sh, and then click Get Started. And then on the left, you should see this Getting Started button. And then click Getting Started with Karpenter. Now, one very important point is you need to have this AWS CLI, kubectl, EKSCTL Helm, but this is the important part. This EKSCTL version needs to be above version 0.165, else the Karpenter installation will fail. I'm using Cloud9. You can use any terminal or any IDE that you like. You can check EKSCTL version by simply running EKSCTL version. And as you could see, I'm using version 0.167. If you have a version which is lower than that, you can click these links. Then you can go and install and upgrade all these packages. So the next step is to create the EKS cluster. So for that, we need to set these environment variables and then create a cluster. So what I'm going to do is I'm just going to fast forward these steps because those are just regular steps. And then I'm going to go in detail when we install Karpenter. All right, with that being said, let me just go ahead and create a EKS cluster. All right, my cluster is up and running. Like I said before, I just copy pasted from the guide itself, set the environment variables, and then create the cluster. It will take around 10 minutes for the cluster to come up. All right, so at this point, we are all set to install Karpenter. AWS makes it easy to install Karpenter because they published the Helm chart for Karpenter in the public ECR. All right, so I'm just gonna copy these commands as well, go back to my Cloud9 command terminal, and then paste it here. So this will take around 1 minute or so. All right, Karpenter is installed. Next, let's create our NodePool. So if I scroll down, this is the YAML for the NodePool, as well as it's creating a EC2 node class. At this point, we should be able to understand this NodePool and EC2 node class. So basically, this NodePool is only provisioning AMD 64 or x86 instance type, operating systems Linux, only Spot instance category of C, M, and R, instance generation greater than 2, and then node class it's referencing EC2 node class with the name default. So this EC2 node class with the name default. But before we go there, limits is 1000 core. So this node pool will keep on provisioning EC2 till all the CPU cores that it has provisioned across all the instances reaches the limit 1000. And it also has a disruption policy. When underutilized, it will consolidate those nodes, and every node will expire after 720 hours, which is 30 days. So 30 days multiplied by 24 hours. All right, EC2 node class default. AMI family is AL2, and we don't have any AMI selector. That means it is using EKS optimized AMI for AL2. And then the IAM role for the EC2 is Karpenter node role dash this variable name. This is created when we created the cluster using EKSCTL. Then it's selecting the subnet with the tag karpenter.sh/discovery, and then the cluster name and the security group similar way. So if we scroll up in the EKSCTL, it should be tagging all those. All right, so you can see it's creating this Karpenter node role with the cluster name. And here we go. The cluster config, the tags karpenter.sh/discovery, and then the cluster name. So it's attaching this tag to every subnet and every security group this CloudFormation is creating. If you already have existing subnets and security groups and you want to use this NodePool and EC2 node class, you need to ensure that you go and tag them with these tags. Or if you use your own tag, you need to come here and change the role and the tags to match what's in this YAML. But for simplicity, we keep everything as is. We're simply gonna copy this and go to our terminal and then run this. All right, so the NodePool and EC2 node class is created. So if I run kubectl get NodePool, all right, so we could see the default NodePool has been created. And at this point, you can run any kubectl commands because this is a Kubernetes object. So for example, if you want to see this NodePool, so basically kubectl describe NodePool default the same way you describe a pod or any other default Kubernetes object, right? So it describes the NodePool. You can do kubectl get NodePool default -o YAML. All right, and it's going to show the NodePool, and you can dump it into YAML, all that good stuff. One important thing to keep in mind is if no conditions are satisfied, then no nodes will be provisioned, especially for EC2 node class. So you want to make sure there are AMIs or security groups, subnets that are, or instance role that is being selected by this specification. So how do we do that? So we do that by running describe command on the EC2 node class. But first, if we do kubectl get EC2 node class, and it should come up as default. Similar way we did the NodePool. Our commands also created EC2 node class with the name default. So now if you run kubectl describe EC2 node class default, okay, on the bottom there is this status field. So on the top you have the stuff related to what you define, that AMI family is AL2, and then some extra stuff, role, security group selected term, etc. But the status field will show what are the AMI, security group, subnets, roles that are being satisfied, right? So let's say, for example, for our AMI, we put AL2. So it's going to give us all the AMIs that's being satisfied by that condition. So it's giving a ARM64 node, which is a Graviton node, which is AL2. It's giving a GPU node, which is AL2. It's giving another variation of the GPU node with the accelerator. And finally, it's giving a node, which is x86, a regular node. So as you could see, whatever condition we put for AMI, it's actually selecting 4 different AMIs. So we are good for AMI. Similarly, the instance profile, it's actually giving us the actual instance profile, whatever the name is. Even though we used variable, it actually resolves into an actual instance profile. Security group, similarly, it shows that it's going to select these 2 security group, and then subnet, these are the applicable subnets where EC2s will be provisioned. Okay, so now we know that whatever we put for EC2 node class, we are going to have EC2 up and running because we have a bunch of options that it can choose from. All right, next we are going to scale the nodes. But first, let's see how many nodes are running. So if I run kubectl get nodes, there are 2 nodes running. Now let me go back to the guide. So the way we are going to scale is, we are not going to use horizontal pod autoscaler. We are simply going to increase the replicas. So basically, this is hard coding the number of replicas. Generally, with actual application, horizontal pod autoscaler increase the replica. In this case, we are just going to use the Kubernetes command kubectl scale, and we are just going to increase the number of pods in the replica. And then at that point, the existing EC2s cannot accommodate it, and Karpenter will trigger creating new EC2s. Okay, so I'm just going to copy this. And the last command is kubectl logs. It's going to read the logs for the Karpenter deployment. Remember, Karpenter is deployed as a pod as well. So it's just going to show the logs. And then there we should see that Karpenter is scaling nodes. All right, let's copy this and then going to paste it. All right, let's see. It's gonna take a few seconds. All right, so you could see within like a second or two, it's actually launching it. So instance type M6 2x large, capacity type spot. If I do Control C, it quits it. And then if I do kubectl get pods, all right, so you could see the containers are creating. So they were pending, and then Karpenter launched the nodes, and now these pods got scheduled by the scheduler, and now the container is creating, and soon they will be running. Here we go. So let's do kubectl get nodes. Okay, so you could see that it went up from 2 nodes to 3 nodes. And you could see the age is 43 seconds. So this is the node that Karpenter brought up. So let's inspect the nodes in a little bit more detail. If I go to my EC2 console, this is the node. I identified it based on the IP address as well as the status check. It says initializing. So if I go to tags, okay, it attaches the cluster name EC2 user Karpenter demo, managed by EC2 user Karpenter demo. It also attaches the name of the node pool, which is default, karpenter.kubernetes.aws/EC2 node class default. Okay, so Karpenter attaches all this stuff. Now let's inspect this node for labels, and we should see a little bit more information. So if we go back to terminal and run kubectl get nodes -- show labels equal to true. All right, so it shows the label of all 3 instances. But by the edge, you could tell this is the newly provisioned instance. You could see this is a spot instance based on our node pool. Any EC2 that a Karpenter node pool provisions, it will attach the name of the node pool to it. So in our case, the name of the node pool, we kept it as default. So you could see karpenter.sh/nodepool equal to default is added as a label. So you can use this to schedule pods, or you could even add custom labels, which we will do in a later lecture and a later demo. All right, if I go back to the guide, we can simply scale down the deployment, and that additional node should be terminated. Okay, I'm just again copy this scale down, go back here. Okay, I'm just going to Control C. We don't need to see the logs because we know what's going on. kubectl get pods. Wow, it is quick. It already affected the pod. All right, if I go to my EC2 console, you could see this node is shutting down. All right, first Karpenter demo in the books. I am not going to delete the Karpenter nodes or delete the cluster because I'm going to use this for the other demo. But if you are just testing this out, remember you will incur charge if you don't delete it. So if you want, go ahead and delete the nodes where Karpenter is installed, as well as delete the cluster. All right, that's it for this one. I'll see you guys and girls in the next one. Bye. Welcome guys and girls to this lecture. In this lecture, we're going to learn how Karpenter optimizes cost using a feature called consolidation. So let's say your Kubernetes cluster worker nodes are looking like this. So over time, you have 4 EC2 worker nodes running. Now the first worker node is really running efficiently. All the pods are bin packed, they're like packed tightly, there is no resource misutilization. However, the last 3 EC2 worker nodes, not so much. There is a decent amount of resource misutilization, there are a lot of empty space. And you may be thinking, how does this cluster worker nodes look like this? Well, it can happen that over time, the traffic increased and horizontal pod autoscaler created a lot of pods, and Karpenter provisioned 4 nodes, and at one point all 4 nodes had 4 pods each. We are assuming that each EC2 can have up to 4 application pods, and then as the traffic went down, some pods got terminated, and the EC2s ended up looking like this. So with Karpenter in the node pool, you can simply turn on this flag, disruption and consolidation policy when underutilized. And Karpenter will automatically detect that some of the EC2s are underutilized, and it will bin pack those pods. So in this case, it moved the pods from the last 2 EC2 instances onto the second one, and then terminates the third and fourth EC2 instances, which means better utilization of worker nodes leading to reduced cost. Not only that, so let's consider another scenario. In this case, the second and third worker nodes are M5.extra large, and even if Karpenter bin packs these two pods into one EC2 instance, there will still be misuse of resources, right? Because still 50% of the EC2 will be not utilized. So Karpenter is smart enough that it actually creates a new EC2 instance, M5.large instead of M5.extra large, and then it puts those two pods from two larger instances into this newly provisioned instance. So in this case, Karpenter is getting rid of both the nodes and launching a node half the size to accommodate both pods. So a better selection of worker nodes leading to reduced cost. So let's take a closer look at the NodePool YAML for consolidation. So Karpenter works to reduce cluster cost by removing empty nodes, removing nodes by moving the pods to another underutilized nodes, or replacing nodes with cheaper variants. And you turn this consolidation feature on by specifying them under this disruption field. You can specify consolidate after. So even if a EC2 is underutilized, Karpenter will wait this many seconds before it disrupts the node. And the consolidation policy could be when empty or when underutilized. When empty, as the name suggests, Karpenter will only consider nodes for consolidation that contains no workload pods. It's okay if you're running system pods or a daemon set, but Karpenter will only consider that empty if there are no workload pods or application pods running. So in this case, when the EC2 is empty, Karpenter will wait additional 30 seconds before terminating the instance. Other option is when underutilized, Karpenter will attempt to remove or replace nodes when a node is underutilized and could be changed to reduce cost. And if you are noticing another field expire after under the same disruption field, that is not related to consolidation. So consolidation, expiration, they are different kinds of disruption. So we are going to learn about the other kinds of disruption, including expiration, in a separate lecture. But the consolidation has these two options: consolidate after and consolidation policy. Another variation, you can skip the consolidate after. You can just put disruption, consolidation policy when underutilized. All right, so this is how out of the box you just enable a flag and Karpenter will start saving you money. Some of you may be thinking that you don't want certain nodes or certain pods to be consolidated. So even if the node is very underutilized or empty, you don't want to be terminated. Maybe you have a reason to keep that node up and running. So there are ways to control these different kinds of disruptions, such as consolidation, expiration, drift, etc. So once we go through the normal behavior of these different disruptions in the next few lectures, we are going to learn how you can control this disruption in case you don't want to be disrupted. That's it for this one. I'll see you guys and girls in the next lecture. Bye. Hey folks, Raj here. This is the first 1 hour covering the fundamentals from my Karpenter Masterclass course. In the full course, we go over all the Karpenter concepts needed to run your real-world workloads with Karpenter. The full course covers from basics to advanced topics. You get a certificate of completion. It also has a 14-day money-back guarantee. The course covers real-world topics like how do you do scheduled and pre-warmed scaling with Karpenter, Karpenter per namespace for multi-tenant cluster, migrating from cluster Autoscaler to Karpenter, Karpenter best practices, and up-to-date quizzes. I have included a discounted link in the description. As always, thanks for watching this video. If you found this video helpful, please click the like button and share this channel with your friends and family.